And this is now the Lorentz gauge. According to Lorentz gauge, F divergence of A plus 1 over C square partial V divided by partial T, which is equal to 0. I think this term in equation number 2, if we consider this is equal to 0, then this is the Lorentz condition. The Lorentz gauge condition. Then this divergence of A, which is equal to minus 1 over C square partial V divided by partial T, and this, the divergence will be equal to, divergence of A will be equal to minus 1 over C square partial V divided by partial T. Now, putting this value in equation number first, equation 1 implies that del square V plus partial divided by partial T, and the divergence is minus 1 over C delta V divided by this one and minus rho divided by epsilon naught. And here we can get del square minus 1 over C square and partial square V divided by partial T square, which is equal to minus rho divided by epsilon naught. If we take V common, then del square minus 1 over C square partial square divided by partial T square V, which is equal to minus rho divided by epsilon naught. And this operator, this shows the space and this shows the time. So this is a space-time, and we can represent this D'Alembert or D'Alembert operator, and it is denoted by this. Time we have discussed about this in detail. So this equation D'Alembert square V, which is equal to this, and this is nothing but this is the n-homogeneous wave equation. Wave equation. Similarly, putting this is equal to 0, already if we put the value of divergence, then this will cancel out with this, and this term will be equal to 0. And similarly, equation 2 implies that del square A minus mu naught epsilon naught del square A divided by del T square minus del, and divergence, the condition is the divergence which is equal to minus 1 over C square partial V divided by partial T, that last time we have obtained this, and this is mu naught epsilon naught partial V divided by partial T, which is equal to minus mu naught J. You can put this is equal to 0 as well, no problem. Mu naught epsilon naught, this is 1 over C square, so this will cancel out, and we have del square. This is del square. A can be taken out from this side. mu naught epsilon naught partial square divided by partial t square and a, which is equal to minus mu naught j. And mu naught epsilon naught, this is 1 over c square. So this is again D'Alembert, and this D'Alembert operator square a, which is equal to minus mu naught j. So this is still the n homogeneous equation. So we have these two equations. Which is equal to minus mu naught j. This is also an homogeneous wave equation. Now we have two inhomogeneous wave equations for V and A. And this is actually the 4-dimension Poisson equation. Are 4-dimension Poisson equations. Because in 4-dimension, one is del, which is a space part, and the other one is the time, so space-time, and this is a 4-dimension Poisson equation. In the 3-dimension Poisson equation, we have already know about del square V, which is equal to minus rho divided by epsilon naught. So this is only related with space, so this is the 3-dimension. Here in the D'Alembert, we have a time as well. Then this is a 4-dimension Poisson equations. And these equations can be solved very easily to find out the value of V and A. And then we can calculate the electric field and magnetic field very easily. So this is the case. This is the Lorentz gauge. Now the Lorentz gauge is more convenient as compared to the Coulomb gauge, because in the Coulomb gauge one cannot find the vector potential very easily. And here in this Lorentz gauge, we have the Poisson equation, and the Poisson equation can be solved very easily, and one can find out the value of V and A. And if we find the value of V and A, then we can find out the electric field and magnetic field very easily.